Good afternoon to all of you all. In this video, we wish to see how we can check whether a wave pulse in a string is symmetric or not. We are given 5 examples of a wave pulse. If you observe each of these, you will find that y is a function of x as well as t. T is the time and x is the distance of a point of the string from the free end of the string. The free end of the string is the source from where the disturbance originates. So now you find that y is a function of x and t, but x and t are they figure in the equation in a very special way. You will find that it is something like ax plus bt plus c. It's always of this form. Yes, this could be squared or whatever, but x and t figure in this linear combination ax plus bt plus c. A could be positive or negative, B could be positive or negative, similarly C could be positive or negative, or C could be 0 as well. But A and B cannot be 0. Yes, and if you see here, you find 2x minus 4t plus 4. So A is 2, B is minus 4, C is 4. Here if you compare this, you will have A as 1 by A and T as minus 1 by T. C is 0. Here again it is the same thing, except that here there is no square, but this whole thing is, this power itself is squared. Here you have B as 4 plus 4 and A as minus 3. AX minus AX plus BT. Yes. And here you have A as 3, B as 4 and C as minus 6. So they always figure in this fashion. In any wave equation, whether it is a wave pulse or a wave train, they will AX plus BT plus C has to occur together in this linear form. Now, the speed of the wave is given by minus b by a. So if you take the first equation, you take the first wave equation, so the speed would be minus b is minus 4 by 2. 2 is plus 2. So you get 2 meters per second, assuming everything is in SI units. Now you get plus 2. We must note that whenever A and B are of opposite signs, the wave travels in the positive x direction. So you get the speed as plus 2 meters per second. Similarly, you can check for the others. The speed in the second case, the speed would be minus 1 by t by 1 by a, or that will be a by t. A by t is the speed. Same is true in the third case also. The speed is a by t. The fourth case, the speed would be b by a. B is now 4. Yes, bt. B is 4. So the speed would be minus 4 by minus 3. So minus plus 4 by minus 3. So that is 4 by 3 meters per second. Similarly, in the fifth case, it will be minus b. B is 4 plus 4 and b is plus 4 and you have a as plus 3. So the speed is minus 4 by 3. So all these waves are moving in the positive x direction. Positive x direction. This is also positive x direction. this is positive x direction, whereas this is in the negative x direction. Whenever A and B have the same sign, that is, if both are positive or both are negative, the wave travels in the negative x direction. When A and B are having opposite signs, the wave travels in the positive x direction. Yes. So now let us see how to check whether this graph, whether this waveform is symmetric or not. To check whether it is symmetric or not, the first thing we must note is that there must exist a local maxima or a local minima. So how do we find a local maxima or a local minima? Now if you take the first example, y is equal to 10 by 2 plus 2x minus 4t plus 4 the whole square. Now you must note that this quantity can be greater than 0 or equal to 0. Right? So why now the displacement of the string, the vertical displacement of the string will be maximum when this quantity is minimum. The minimum value this can take is 0. So y max is 5. So because there is a local maximum, we say that we can check for symmetry. If there is no local maxima or minima, then there will not be any symmetry, as we shall see in the other examples. So y max is 5. Now what we need to do is we need to find out what is x at y max. What is x? X at y max is how much? At some instant. At some or any instant. At some instant or at any instant of our choice. So let us take the instant as 0. Let us say we want to find out at t equal to 0. So if you put t equal to 0 in this, and this whole thing is 0, yes, t is 0, we have chosen t as 0, and anyway this quantity is 0 because we want to find y max. So 2x plus 4 is 0, or x equal to minus 2. So therefore the maximum occurs at x equal to minus 2 at the instant t equals 0. So now we need to check. So we know that is a maximum like this, and this is at minus 2. This maximum value is 5 plus 5. Now what we need to do is we need to check if we go to the right by a certain distance delta x, y will change and there will be a certain value. If we go to the left, that is go at minus delta x, y will have a certain value. If this value and this value are the same for any delta x, then we can say that the pulse or the waveform is symmetric. Yes. So let us do that. We have y is equal to 10 by 2 plus. Now we are checking for the maximum. Yes, we are checking for the maximum. So let us see 2x minus 4t plus 4. 2x minus 4t plus 4 the whole square. If you see this, just a minute, I'll write this. Y is equal to 10 by 2 plus 2 into the maximum occurs at minus 2. So we will put minus 2 plus minus delta t plus minus delta x minus 4 into 0 because the instant is 0 plus 4 the whole square. So if you simplify this, see what you get. You get 10 by 2 plus 2 into minus 2 is minus 4. It will be plus minus 2 delta x. This is 0 and you have plus 4 the whole square. plus 4 and minus 4 cancels, and therefore you have y is equals 10 by 2 plus 2 delta x the whole squared or 4 delta x squared. So you find that y will have the same value whether delta x is plus delta x or minus delta x. It will not make a difference, and hence we can conclude that the pulse is symmetric. Yes, this is a symmetric pulse. We could have done this at some other instant also. Let us say we do this at a different instant. Let us say t equal to 1 second. Supposing you take t as 1 second, you take t as 1 second, put t as 1 here, minus 4 and plus 4 will cancel. So y will be equal to 2 by 2 plus 2x the whole square. Now y will be maximum at x equal to 0. Yeah? So all that you need to check is y at 10 by 2 plus 2 into x is 0. So choose that x at which y is maximum plus minus delta x the whole square. So this will again give you 10 by 2 plus 4 delta x squared, 2 delta x squared. So again you find that whether delta x is positive or negative, y will have the same value. So therefore again we come to the conclusion that that the pulse is symmetric. You can do it at any instant. You can do it, the most convenient instant is t equals 0. It involves less calculations. Whereas you can do it at any instant because the shape of the pulse is not going to change as it moves along the string. Yes. So therefore you can do it at any instant. Now if you see this, you see how the graph looks. If you plot y versus x, let's say at t equals 0, the maxima was at minus 2. We saw that. Put t equals 0, 2x plus 4 is 0, so x is minus 2. So there is a maxima here like that. Yes, and it is symmetric. We proved that it is symmetric. This is 5. This is 5. Yes. Now, at x equal to 0, again the maximum occurs. So the maxima is somewhere here. This is at t equals 0. This is at t equals 1 second. Yes, at t equal to 1 second, the pulse has moved to the right. Remember, it is 2x minus 4t. The sign of A and B are opposite. So the wave travels along the positive x direction. So it has moved from here to here. We can get what the speed is. It has moved by a distance of 2 meters in 1 second. So the speed is 2 meters per second. As we already saw, minus b by a minus 4 by 2 meters per second. Yes. Now take the second example. If you take the second example, let us take the instant t equals 0 for convenience. So you have y is equal to a into e power minus x by a. So y will be a by e power x by a. So as x increases on the positive side from 0, y will keep on decreasing. Yes, y will keep on decreasing. And at x equal to 0, y is a. So if you plot the graph of y versus x, it would be a at x equal to 0, and as x tends to infinity, y will tend to 0. So the graph will be like this. Now x is negative, yes, if x is negative, then y would be more than a, and the graph is going to extend like this, and as x tends to minus infinity, y will tend to plus infinity. So there is no local maxima or minima. Okay, so therefore this graph is, this pulse is, this waveform will be asymmetric. Yes, this is a case of asymmetry. But if you take the third example where we have just put a square here, now what is going to happen is once you square it, you will have a square term here, and even when x is negative, the value is going to be the same because it is squared. So therefore this graph would now be like this. Yes, so if you square it as in the third example, the pulse would become symmetric. So this is symmetric, whereas the second example is an asymmetric one. Take the fourth example. The fourth example, let us again take t equals 0. So if you take t equals 0, you will have, this is fourth one, y1 is equal to 5 by 9 x squared plus 2. Now y1 will be maximum at x equal to 0. Yes, y1 will be maximum at x equal to 0. Put x equal to 0 and y1 max will be equal to 2.5. 5 by 2. When x is 0, 5 by 2, that will be y1 max. Now check for symmetry. Y1 should be 5 by 9 into the maxima occurs at x equal to 0. So 0 plus minus delta x, the whole square plus 2. That will be 5 by 9 delta x squared plus 2. So whether delta x is positive or negative, okay, so it doesn't matter. Y1 will have the same value. Therefore, this is symmetric. This will be a symmetric pulse. Similarly, for the next one, for the fifth one. Okay, let's draw this. Let's draw this pulse. The y max is 2.5. We are plotting y1. Y max is 2.5 at x equal to 0. This is at instant t equals 0. Yes. So what would happen? As x tends to infinity, y1 will tend to 0. So this will tend to 0. And x tends to minus infinity, this will tend to 0. That is the graph of y1 versus x. In the fifth example, you will have a minimum, because when this quantity 3x plus 4t minus 6 is 0, this can't be negative because it is squared. So the minimum value this can take is 0. So the denominator will be minimum. So 5 by the minimum value, the modulus value or the absolute value will be maximum. Because there is a negative sign, it is a case of minimum. So y2 will be minimum, that value is minus 2.5. Minimum value of y2 is minus 2.5. Now what we can do is check where this minimum occurs. Choose any instant. Again, let us take t equals 0. If you put t equals 0 and make 3h minus 6 equal to 0, you get x equal to 2. So x will be equal to 2. Therefore, the minima occurs at x equal to 2. How will this graph look? If you see this, okay, now let us check whether it is symmetric or not. To check whether it is symmetric or not, y2 is equal to 5 by 3 into x is 2 plus minus delta x, the whole square, plus minus delta x plus 4t minus 6 the whole square plus 2. 3x plus minus delta x. Now if you t is 0, because I have taken instant t equals 0, put t as 0, you will have 3 into 2 6. 6 will cancel with the minus 6 and you will have 9 delta x squared by 2. Yes, y2 will be minus, there is a minus here, minus 5 by 3 into 3 2s are 6. 6 will cancel with the minus 6. You will have 9 delta x squared plus 2. So y2 will be minus 5 by 9 delta x squared plus 2. Again you find that this pulse is also symmetric. Whether you take plus delta x or minus delta x, y2 will have the same value. So both these graphs are symmetric. Let us try drawing this on the same string. Supposing both these are on the same string, what happens? If both these are on the same string, you will have this like that, and this tending to infinity, this tending to infinity. You will have at 2, you have a minimum, and this will go this way. Yes, this is how graph will be. This will be minus 2.5. At the same instant t equals 0. So both these pulses, we are showing it on the same string. Let us say we have created two pulses on the string. Now let's see how these are moving. If you see the first one is moving at minus b by a. So minus b by a will be minus b is plus 4, a is minus 3, so plus 4 by 3. So this is moving at 4 by 3 in the positive x direction, 4 by 3 meters a second. So what about this? If you see this, it will be minus plus 4 by plus 3, plus 4 by plus 3. So that will be minus 4 by 3. So this is moving at 4 by 3 to the left. So obviously when these two are crossing each other, there is going to be superposition of both these, and there will be a resultant displacement. Yes, there will be a resultant displacement. Let us see whether the resultant displacement cancel each other everywhere and at all times. To check that, what we are essentially saying is y1 equal to y2 for all times and everywhere? This is the question we are having. Is y1 equal to y2 at all times and everywhere? Well, if y1 has to be equal to y2, that is y1 equal and opposite. Or we are saying is magnitude of y1 equal to magnitude of y2 for all times and everywhere. Yes, the other, so we will ignore the negative sign. We know they are on the opposite sides. This is above the x-axis, this is below the x-axis. So whether this holds good, that means phi by, if you equate these two, what you are going to essentially get is 4t minus 3x the whole square plus 2 equals 3x plus 4t minus 6 the whole square plus 2. So if you simplify this, 2 cancels, take the square root, you will get 4t minus 3x is equal to plus or minus 3x plus 4t minus 6. Let us see what we get if we solve this equation. So you take 4t minus 3t and the plus sign is equal to 4t minus 3x 4t minus 3x is equal to, take the plus sign, plus 3x plus 4t minus 6. Yes, we have equated these two. So 4t will cancel, and you get 6 is equal to 6x, or x equal to 1. So we find that at x equal to 1, at all instants, at x equal to 1, at all instants, yeah, y1 will be equal to y2. Check that. Y1 is 5y. Put x equal to 1, you will get 4t minus 3 the whole square plus 2. What is y2? Y2 will be minus 5 by x equal to 1, minus 6 and plus 3 is minus 3. So you will have 4t minus 3 the whole square plus 2. So therefore you find that at x equal to 1, y1 and y2 are always equal and opposite for any time that you may choose. So for all times, the displacements y1 and y2 cancel each other at x equal to 1. Let us take the other equation. 4t minus 3x is equal to minus 3x plus 4t minus 6. So here you will have this as minus 3x minus 4t plus 6. Yes. Minus 3x minus 4t plus 6. So 3x will cancel and you get 8t equal to 6, or t equal to 3 by 4 seconds. So at t equals 3 by 4 seconds, okay, whatever be the value of x, y1 and y2 will be equal to each other and the two pulses will cancel each other. You can check that. Put t equals 3 by 4 in this. If you put t equals 3 by 4 in this, 5y. If you put 3 by 4, you will get 3 minus 3x the whole square plus 2. What will be y2? Y2 will be minus 5y. Put t as 3 by 4. So you will get 3 here. 3 minus 6 is minus 3. So you will have 3x minus 3 the whole square plus 2. So whatever be the value of x, the denominator is going to be the same. Yes. So y1 and y2 will cancel each other everywhere on the string at t equals 3 by 4. In fact, you can see 3 equal at time t equal to 3 by 4, the two pulses, the maxima and the minima of the pulse will coincide at x equal to 1. At x equal to 1. Yes, at x equal to 1, both the maximas are at x equal to 1, at all instants it was cancelling. So even at t equals 3 by 4, it must cancel. So at x equal to 1, you find that the two pulses will cancel each other fully. Okay, you can see the time also. The distance between these two pulses is 2 meters. This is moving at 4 by 3 and this is moving at 4 by 3. So the relative velocity is 8 by 3. 8 by 3 meters per second. So you simplify this, 2 fours are, you get 3 by 4 seconds. So at 3 by 4 seconds, they will have, they will be one over the other. Yes, one over the other, and they will fully cancel each other. Both these pulses are symmetric. Not only symmetric, they are identical. Thank you.